Let's now look at the size of the probe in the scanning electron microscope. We've seen that the size of the probe determines the area or the volume in the sample from which signal is generated. So the probe size ultimately determines the resolution in our scanning electron microscopy approach. Now, obviously, the first contributing factor to the size of the probe is diffraction. It is the fundamental limitation. But next to diffraction, there are other factors playing a role here. We have seen before that aberrations add up to the diffraction-limited size of the probe. And again, we have spherical aberration and chromatic aberration contributing to the probe size. But there's a fourth factor. It may not be so obvious, but this relates to the fact that we have to take electrons from the source, and there at the source they appear from a certain physical area, which we call the virtual size of the source, the virtual source size. Now, what the electron microscope system does, all the lenses, is they demagnify this virtual source size onto the sample, and thus the size of the source, the virtual size of the source, together with the demagnification factor of a microscope, also limits the achievable size of the probe. Now, these four contributions depend on several factors. An important factor is the opening angle of the beam in the image plane, the beam opening angle. So for diffraction, we know that the diffraction-limited size of the probe relates to the wavelength of the electron, so the energy at which it traveled, divided by twice the opening angle of the beam. Note that here we take into consideration that the beam opening angles in an electron microscope are small, typically on the order of a few milliradians or 10 milliradians. And in this case, we can equate the sine of the opening angle to the value of the opening angle itself, where again we have to consider that we calculate in radians. So if we increase the opening angle of the beam, the diffraction contribution to the probe size decreases. Now, for spherical aberration, we have seen that the spherical aberrated probe size contribution depends on a lens or lens system specific factor, the spherical aberration coefficient. This spherical aberration coefficient is multiplied by the opening angle of the beam cubed. So spherical aberration contribution grows if we increase the opening angle of our beam. It grows drastically. This is one of the main reasons why in scanning electron microscopy we keep the opening angle small. Also, chromatic aberration increases with the opening angle, but in a linear fashion. In addition, we have a lens-specific factor again, the chromatic aberration coefficient, CC, and of course we have a quantity characterizing the energy dispersion in our probe. This factor is the width of the energy distribution divided by the average energy of the electrons in the beam, E0. So, if we increase the energy of the electrons, so if we work at higher voltage, the chromatic aberration decreases. This is why in high-resolution transmission electron microscopy we work at energies of 100 to 300 kiloelectron volt. Then finally we have the contribution of the source size. This is simply given by the magnification of the electron microscope system, or better, demagnification, times the virtual source size. And the magnification factor, of course, also depends on the opening angles of the system. It's the object plane opening angle divided by the image plane opening angle. So again, we see that the source size contribution decreases if we increase the opening angle of the beam. Now we have to look, when we are determining the final probe size, how these different probe size contributions add up. We know that we have electrons with slightly different angles, different energies, so each of these factors has a certain distribution. Now, if these distributions would be fully independent and Gaussian, we know that the total probe size could be achieved by summing the different contributions in quadrature and then taking the square root. However, in electron microscopy, this is not that simple. These distributions are typically not Gaussian. A full equation has been derived, which you see depicted here, which is quite complicated, and you don't have to know this by heart. The only thing you have to know is that these different contributions add up, but not in similar linear fashion, also not in simple quadrature fashion, but in a slightly different fashion.